2,300 light-years away, there's an object orbiting so close to a dead star that its entire year lasts less than 8 hours. Gravity has crushed it into the shape of a lemon. Its atmosphere is made of something that, by every rule of planet formation we currently understand, should not exist. And when the scientists who found it finally looked at the data, their first reaction wasn't excitement. It was confusion. Their exact words were, "What the heck is this?" This is the story of the strangest planet NASA's James Webb Space Telescope has ever observed. A world that doesn't just break the mold of what a planet is supposed to look like, but actively defies every known explanation for how it could have formed in the first place. To understand how strange this discovery really is, you first need to understand what it's orbiting, because the star at the center of this system is almost as bizarre as the planet itself. It's called PSR J23222650, and it is not a star in any conventional sense. It's a pulsar, the collapsed remnant of a star that once lived and died in a supernova, leaving behind a core so dense and so compact that, in the words of lead researcher Michael Zhang of the University of Chicago, it carries roughly the mass of our sun packed into an object the size of a city. Pulsars spin at extraordinary speeds, some completing a full rotation in mere milliseconds, and as they spin, they blast twin beams of radiation out from their magnetic poles like a cosmic lighthouse sweeping across the galaxy. In this particular system, that radiation comes almost entirely in the form of gamma rays and other high-energy particles, wavelengths completely invisible to Webb's infrared instruments. Which means, in a strange twist, astronomers can study the planet orbiting this pulsar in extraordinary detail across its entire orbit, without the blinding interference that normally drowns out a planet's faint light in the glare of its host star. Maya Belesne, a graduate student at Stanford who worked on modeling the system, described it as a genuinely unique situation, one where researchers can see the planet fully illuminated without ever actually detecting the star lighting it up. It gives scientists an unusually clean, pristine view into a system that, under almost any other circumstances, would be nearly impossible to study this closely. Now here's where it gets strange. The planet itself, designated PSR J23222650b, sits just a little over 1 million miles from its pulsar. For comparison, Earth orbits our Sun at a distance of about 93 million miles. This planet is roughly 90 times closer to its star than we are to ours, locked into an orbit so tight that a full year, one complete trip around its star, takes just 7.8 hours, not 7.8 days, 7.8 hours. By the time you finish watching a single feature film, this world could have completed nearly 2 full orbits. At that distance, squeezed by gravitational forces from a star far more massive and far denser than anything in our own solar system, the planet isn't even a proper sphere anymore. When the team modeled the brightness variations of the planet as it moved through its orbit, they found that the pulsar's gravity is actively pulling the Jupiter-mass world into a distorted, elongated shape, closer to a lemon than a ball. It's a level of gravitational deformation that simply doesn't occur among the planets we're used to, a visible, measurable reminder that this world is living under conditions our own solar system has no real analog for. But the shape wasn't even the most surprising part. When the team broke down the planet's light into its component wavelengths, using a technique called spectroscopy that lets scientists identify the specific molecules present in a distant atmosphere, they expected to find something at least broadly familiar. Water vapor, maybe methane, perhaps carbon dioxide, the kinds of molecules Webb has identified on dozens of exoplanets before this one. Instead, they found something almost nobody had seen before in any planetary atmosphere: molecular carbon. Specifically, 2 distinct carbon molecules known as C3 and C2, essentially chains of pure carbon atoms bonded directly to each other, dominating an atmosphere otherwise built from helium. Peter Gao, a team member at the Carnegie Earth and Planets Laboratory, described the moment the data came back in blunt, honest terms. The team's collective reaction, he said, was simply, "What the heck is this?" It wasn't hyperbole. It was the genuine response of scientists looking at readings that didn't match anything in the existing catalog of known planetary chemistry. And the implications of that carbon-dominated atmosphere go far beyond simple novelty. Under the crushing pressure inside a planet like this, that abundance of pure carbon opens up a genuinely startling possibility. Deep within the planet, that carbon could be compressed into diamond. Not metaphorically, literally. The pressure and composition inside this world may be capable of forming diamond material at its core, a detail that reads more like the setup of a science fiction story than a peer-reviewed astronomical finding. And yet, it's exactly what the physics of the system suggests. The real mystery, though, isn't just what the planet is made of. It's how something like this could have possibly formed at all. Michael Zhang put it plainly. This extremely carbon-enriched composition seems to rule out every known formation mechanism scientists currently have for building a planet. Normal planets, the kind that form from the leftover disk of gas and dust surrounding a young star, simply don't end up with atmospheres built almost entirely from pure carbon molecules. That's not how planetary chemistry is supposed to work. So the team turned to the other likely explanation, one tied directly to the strange, violent history of the system it's found in. Together, the pulsar and its planet form what astronomers call a black widow system, named quite deliberately after the spider. In a typical black widow pulsar system, a rapidly spinning neutron star is paired with a small, low-mass companion star, and over time, material gets stripped from that companion, streaming onto the pulsar and causing it to spin even faster, which in turn powers an intense outward wind of radiation and particles. That wind then bombards the smaller companion star relentlessly, slowly evaporating it away, layer by layer, the same way the spider it's named for consumes its mate. Astronomers have found other black widow systems before, places where a once normal star has been stripped down to a bare, exposed core by its pulsar partner. It's a violent, but at least previously understood, process. Except this case doesn't fit that explanation either. John was direct about the problem. Even if this object formed by a pulsar stripping away the outer layers of a former companion star, the pure carbon composition still doesn't add up, because nuclear physics simply does not produce pure carbon in the way this atmosphere seems to demand. In other words, the planet doesn't fit the profile of a normal planet forming the usual way, and it doesn't fit the profile of a stripped-down black widow companion either. It sits in some entirely new category, one the team doesn't yet have a clean name for because nothing quite like it has ever been documented before. Roger Romani, a Stanford researcher and one of the world's leading experts on black widow pulsar systems, offered one possible piece of the puzzle, while being careful to frame it as a working theory rather than a settled answer. He proposed that as the companion object cools over time, a mixture of carbon and oxygen inside its interior may begin to crystallize. Because pure carbon crystals are lighter, they could float upward through the interior and mix into the surrounding helium atmosphere, which would explain the strange carbon signature scientists are now seeing from the outside, but that explanation only solves part of the problem. Something, Romani noted, still has to be actively keeping oxygen and nitrogen, elements you'd normally expect to find alongside carbon in a scenario like this, from showing up in the atmosphere at all. And that missing piece, he admitted candidly, is where real scientific disagreement begins. Romani, rather than treating that gap as frustrating, called it something closer to a gift. "It's nice," he said, "not to know everything. It's a genuine puzzle worth chasing." That kind of honesty, admitting the uncertainty rather than papering over it with false confidence, is part of what makes this discovery feel different from a lot of exoplanet headlines. This isn't a case of scientists confidently announcing a fully solved mystery. It's the opposite. It's a team of researchers standing in front of genuinely new data, acknowledging that it breaks their existing models, and being transparent about exactly where their understanding runs out. None of this would have been possible without Webb's specific capabilities, and it's worth pausing on why. Making an observation this precise, isolating the faint light of a Jupiter-mass planet locked in an 8-hour orbit around an object invisible in infrared light, requires an instrument free from the kind of background heat interference that plagues ground-based telescopes. Zhang explained it simply. On Earth, everything around you is warm, and that warmth constantly floods your instruments with extra infrared photons that have to be filtered out and corrected for. Webb doesn't have that problem because it sits nearly 1 million miles from Earth, shielded from the sun by a tennis court-sized sun shield that keeps its instruments at temperatures low enough to detect the faintest possible infrared signals without being drowned out by heat from its own surroundings or from the planet we launched it from. An observation like this one, Zhang noted, simply isn't feasible from the ground. It required Webb specifically, positioned exactly where it is, doing exactly the job it was built to do. The research team, made up of scientists from the University of Chicago, Stanford University, the Carnegie Earth and Planets Laboratory, and the Instituto de Astrofísica de Andalucía in Spain, has submitted their findings for publication in the Astrophysical Journal Letters with funding support from NASA and the Heising-Simons Foundation. And while the paper lays out everything the team has measured with real precision, the central question, how this specific planet actually came to exist in this specific form, remains genuinely open, not glossed over, not quietly resolved in a footnote. Open. What makes a discovery like this one matter isn't just the strangeness of the object itself. Striking as that strangeness is, it's what it represents about the limits of what we thought we understood. For decades, planetary formation models have been built around a relatively small number of known pathways. Planets forming gradually from disks of gas and dust around young stars, or occasionally forming through the slow stripping away of a stellar companion's outer layers. This planet fits neither story cleanly. It sits in the gap between categories, a Jupiter-mass, lemon-shaped world with an atmosphere built from a molecule almost nobody expected to find governing any planet's sky. orbiting the crushed city-sized remnant of a star that died long before this strange companion took its current form. Somewhere out there, 2,300 light-years from Earth, a planet shaped by forces we don't fully understand continues its impossibly fast orbit once every 8 hours around a spinning stellar corpse that may, quite literally, be squeezing carbon into diamond inside a world nobody predicted could exist. And the scientists who found it aren't pretending to have all the answers. They're doing something rarer and honestly more exciting than that. They're telling us, plainly, that they don't know yet and that they can't wait to find out.